looking at you through the glass. Don't know how much time has passed. Oh God, it feels like forever, but no one ever tells you that forever feels like home. Sitting all alone inside your head.
Fair use.
One of the great things that happens during a total solar eclipse is that the sky goes dark and the stars come out. In 1915, Albert Einstein predicted that objects that had strong gravity like the sun would bend light. And Sir Arthur Eddington in 1919 decided to test Einstein's prediction by photographing the stars near the sun during a total solar eclipse. He also photographed them 6 months before the total solar eclipse, when the sun was nowhere near those stars. He then compared the images, and he discovered that just as Einstein had predicted, starlight bent from the gravity of the sun. But he needed a total solar eclipse to do that experiment. Well, we can't bend light measurably on Earth using gravity, but I can show you how to use the bottom of a wine glass to bend light using refraction in very much the same pattern that gravity bends light around the sun or around the galaxy. I've set up a blue light-emitting diode behind me to represent distant stars. And when I move this to the side, you can see a point of light. As I come in, you can see that point of light changing its position. Bending the light from the distant star so you see it from the side. Now the sun doesn't have enough gravity to do this, but a black hole does. If I get exact alignment, the distant star becomes a ring of Einstein rings. It's quite dramatic. But it's probably a good thing that our sun is not a black hole.
Well, that was very interesting. Let me explain to you guys what's really going on. Now, I said in the previous video that why would I even try to convince you otherwise? It was intended, the deception, but you know me. I guess there's a time to deceive and there's a time to reveal and make the ass clown scientards look like fools. So let me do that. Show you what I did here. Playing around with the solar eclipse. Let me pull up a screen here for you guys. Screen. There we go. All right. Get it up there. Okay. What we're looking at, obviously, is a moon in front of the sun with background stars. Now, if I go to my top view here, oops, go to my top view, go to wireframe mode, I'm going to show you what's going on. Okay. Concave Earth, glass skies. You'll notice this yellow glass sphere is surrounding the celestial sphere, the inner sphere there, and then we have the moon sphere, and then we have this larger, the largest of the glass spheres, and they're all have indexes of refraction. At least one has a negative index of refraction. And you'll see this yellow glass sphere. Now imagine if my camera was, it is actually, it's down at the bottom. Let's put it up here. The camera's down there at the bottom, okay. And I got a little sun. That's right over here. There's my sun. It's behind the sun glass sphere, and then the moon is right in front of it. The moon is, or right below it. There's the moon, okay? So the camera's pointing straight at the sun-moon alignment. And what is going on? I was doing a little bit of fiddling around with eclipses in 3D, and what is happening is that because the sun is obviously it's hot, it's going to generate heat and it's going to create thermal expansion of the glass sphere that it's behind. And so it's going to create a bulging. And so let's get that bulging. Right now I have the bulge on the opposite side. You see at the top there's a little bulge. And so if I turn that around, rotate it, so it's directly in front of the sun. Now it's direct, the bulge is right in front of the sun over here. And now we can look through with our camera with the refraction turned on. There's a refraction. Now it's off. Now it's on. So we're always looking at the sun and the moon through glass with refraction. That bulge is actually going to displace the background stars, and that's exactly what they observed, Eddington and Einstein, is that the background stars were displaced as if looking through a glass. Wine glass, yeah, that's the ticket. So what I'm going to do is I'm going to rotate that glass sphere so it's behind again, so we're not looking through the bulge, and you'll see the difference. I'm going to just toggle 180 degrees like that, and then I'll go back to 0. You see the displacement of the stars? That's all that's happening. Thermal expansion is happening because the sun is so hot. Now obviously, if you've ever studied helioseismology, the study of the sun, they will say that the corona of the sun is like exponentially hotter than the photosphere. The photosphere would be the surface of the sun. And so, if you understand what really is going on here, it's the corona that is actually exhibiting most of the heat. Most of the heat is actually going sideways. So it's splaying out like that. And so that's why this glass sphere is not going to melt, because most of the heat is going sideways. If you ever look at a solar eclipse and you see the solar corona, I'll type one in real quick. And you notice how the corona, like this image right here, it shows how the corona is splaying out sideways for the most part. So most of the heat is actually going out sideways like that. But there is still heat in front of it as well. And so that is what's going on here. Also, I was doing some research on the Libyan desert glass, and it exhibits what they call negative viscosity. And when pressure is applied, when heat is applied, the index of refraction changes as well. And so it's going to displace the moon during an eclipse as well. And with the bending of the light, like I mentioned before in a previous video, the way in which the light of the sun hits the back of the moon is only a half of a sphere. Think of like a bowl. And it's paramagnetic, which means it has a very weak magnetic field, and it aligns with the magnetic field. And so this is a new moon over here. When, like the day after the new moon, the light from the sun is still gonna line up with the back of the moon. It's like the moon is like a concave catcher's mitt. It catches the light. That song by Sufjan Stevens, the bowl is filled with light. And so that's what's happening with the moon, and the way the light is interacting, the sunlight is interacting with the moon. The moon, it aligns up the light parallel, and it sucks it up when it's near the sun. But when it's further away, obviously it begins to deviate, and we begin to see the phases of the moon. But that has to do with the magnetism. If you ever watched that video where that guy is putting a magnet to a cathode ray tube, and the light beam or the electron beam from the CRT tube is bending, or it's being repelled by the magnet. Well, this is similar to that, but only the moon being a paramagnetic material is actually aligning. itself with a magnetic field. So we have a few different variables at play here. We have the negative viscosity, which also increases the negative refraction of the glass. It bends the light. It's called the relaxing of the Libyan desert glass. There's actually an article that NASA was a part of. Let's see if I can find that really quick here. I think it's right over here. Relaxation of Libyan desert glass. Evidence for negative viscosity pressure dependence in silica. And look, lo and behold, it's in the Smithsonian Astrophysics, something or other associated with NASA. So yeah, they've studied it. They know what's going on. They know that there's glass above, and it's creating real lensing. It's not gravitational lensing. So that's what's going on with that. Also, I wanted to touch a little bit on solar eclipses. Let's see if I can pull up a file here really quick. Let's see. Let's try this one here. Solar eclipses are going to happen where the shadow of the moon's shadow, moving from west to east, that's going to happen. That only can happen if the sun and the moon are either extremely close to each other, like in my model, or extremely far away from each other, like the Heliotard's model, the spinner model. And so, obviously, if you have any common sense, you realize that the sun is not 93 million miles away. And we can get the shadow moving from, well, I can't do a full traversing of the shadow across the land because I'm limited with the software. I can't do bending light. But what I can do, let's see, where's it going? Here it is. You see how the shadow right here, it's starting on the west side of Africa. And if I scroll, it moves from west to east. And that's only possible if the sun and moon are very close to each other. And so, go back to my top view here. And we see how the sun is right here and the moon is right here. And actually I got two moons there and two suns. One was I was doing a displaced sun and a displaced moon, showing how the refraction actually causes it to move in front of the sun. Let's just, for clarity purposes, let's just eliminate the displaced one so we can see what's going on here. Let's get rid of that one. And let's go back to the sun here and get rid of that one as well. And you also notice too, I put a bunch of lights around the sun. Where was my sun here? I think it was, okay. Zoom in real close. And that was to create a penumbra. If I just have like one light source, it's not going to create the penumbra. So I had to actually outline the diameter of the sun to create that feathered penumbral edge. So that's what's going on with that. Okay. So, yeah, it's hilarious though. I think it's quite amusing to listen to these guys. So, yeah, we're getting a bulge of the glass that's in front of the sun that's creating more of a refraction, so it's, it's displacing the stars, and that's what's happening. I mean, and Einstein got hailed as a hero for coming up with the wrong answer. What do I get hailed as? A moron? A fool? A crazy person? Oh well. Anyway, just thought I'd reveal another groundbreaking secret to y'all. Have a good day.